Alright, this is astronomy video number 2. You can see the questions for today, so there are a few blanks there. Go ahead and fill those out. You can either stop the video or pause it, but go ahead and fill out the question of the day and answer it to the best of your ability. So today we're going to start chapter 24, section 1. It's the study of light. And there are some things that you need to know about light in order to better understand astronomy. The first of which is the electromagnetic spectrum. The definition of the electromagnetic spectrum is that it's the arrangement of electromagnetic radiation according to wavelength. So when I say the term electromagnetic, there are two parts to that. There's the electro part, which is electricity, and then there's the magnetic portion. Okay, so magnetized. And you can see here we have wavelength is from crest to crest, or if we had another trowel, from trowel to trowel. We've talked about that before. So here's kind of a sideways view of the electromagnetic spectrum. We have wavelength on one side, we have long and short. We also have frequency, that's on the other side. We have low and high. So a short wavelength means a high frequency. So we have things on this spectrum that range from gamma rays to X-rays, ultraviolet or UV rays, our visible light portion, which is very small, infrared, microwaves and radar waves, and then television and radio waves. So what is the nature of light? Light behaves kind of like the ocean waves do, or kind of like particles. And we call things, we have small packets of energy that are emitted when we have light that's being kind of shown through the air, and those are photons. So spectroscopy, that's another term. It's the study of light that depends on wavelength. And when we talk about spectroscopy, that's where we get that electromagnetic spectrum. We have what's called a continuous spectrum. And that means it's uninterrupted. It's light that's emitted by a solid, a liquid, or a gas, and it has to be under a certain amount of pressure. We also have the absorption spectrum, and this is produced when you have white light that passes through a very cool gas that's at a very low pressure. And so the gas is going to absorb specific parts of that light, and so the spectrum will look like it has very dark bands within it. So for example, continuous spectrum, there's nothing that's breaking it up. Absorption, you have those black bands intermittently that's kind of breaking things up. And then opposite of that, we have the emission spectrum, where it's a series of bright lines produced by a hot gas that's under low pressure. So this shows you the colors where the black lines would be for an absorption. So this is emitting color, this is absorbing it. So here's another spectrum. You can see we have some absorption here. We have several that are emission spectrums. All of these are for different gases. So this is the sun. This is our visible light ray or light spectrum that we see. For hydrogen gas, helium gas, mercury, and uranium. So when the spectrum of a star is studied, you can actually see a spectral line just like the past ones that we saw, and it's kind of like fingerprints for the stars. So each one of them can be identified based on the elements that are in that star, and it can tell you what they're made of. So how is a spectra formed? You have some kind of an incandescent, either solid or a gas, and it passes through this small slit, and as it passes through, it hits a prism and it creates your spectrum. And once we put a gas, whether cool or hot, in front of that, it changes how the spectra turns out at the end. So again, you have your continuous, your absorption, and your emission spectrums. Doppler effect is something you need to know. It's the apparent change in frequency of waves, and it's caused by the motion of either the source or the observer or both. Okay, so for example, here you see an ambulance that is approaching. So as it approaches, this wavelength gets shorter and shorter, so it's going to get louder and louder. Okay, but as it goes away from you, the wavelengths are getting longer. It's going to get lower and lower in sound. So the Doppler effect is actually used to determine whether a star or any body in space for that matter is moving away from the Earth or toward the Earth. And the majority of objects that surround the Earth that are in our galaxy are actually moving away from the Earth. So it's said that our galaxy is expanding. Chapter 24, Section 2, what kind of tools can we use to study space? The first thing is a refracting telescope, and it uses a lens that will bend or refract light. Refract just means for light to be bent. Okay, and as you can see, we have a lens here. Light is bent as it comes in, and it focuses to one singular point. So the Keck telescope, that's a great example of a refracted telescope. We also have reflecting telescopes. So just like it says, it bounces off of mirrors. So it's using light, concave mirrors, and it's focusing the images with those mirrors. Okay, so you can see we have light coming in, it bounces off of one mirror, it hits onto another, and then you can see it from the side. So a couple of things both refracting and reflecting telescopes have. They both have light gathering power, they both have a resolving power, and they both have a magnifying power. Another type of telescope, or another way that we can study space, is with a radio telescope. It's designed to make observations in radio wavelengths. So these are at really low frequencies, but at a really high or really long wavelength. So what this actually does is it focuses those incoming radio waves to an antenna. It's going to absorb and then transmit those waves into what we call an amplifier. So a lot like how an electric guitar works. It's focusing in all of those electronic signals and amplifying the sound. We also have space telescopes. These are orbiting above our atmosphere. It produces a much clearer image than any of the telescopes that we have here on Earth, because we're having to look through our atmosphere, whereas these have a very clear view. The Hubble Space Telescope is a great example. It was the very first one. It was built by NASA, and it was put into orbit in April of 1990. You can see an image of it here. A couple other examples. We have the Chandra X-ray Observatory Telescope. It was launched in 1999. It was to study X-rays, so that specific wavelength in space and on Earth. We also have the Compton Gamma Ray Observatory Telescope. It's used to study visible light and gamma rays, so it's set for those two wavelengths. Now, we also have another telescope that's going to be coming out hopefully by 2018. That's NASA is planning to launch. It's called the James Webb Space Telescope, and it's going to study infrared rays, or infrared radiation, which aside from UV is the closest in wavelength to our visible light. And that's it for this section.